Today I'm going to explain quantum numbers. I like to think of quantum numbers sort of like if I have a ticket to a game. So if I was going to a Steeler game, I would have a ticket, and that ticket would tell me some information on where my seat is. So I would have something like a gate number, and then it would tell me what section I'm in, and then it would tell me the row, and then it would tell me the seat. Quantum numbers are really similar to that. So if I'm looking at sodium, its outermost electron has the seat numbers right there. So we did orbital diagrams in my previous video, and these are the seats that the electrons could be in. So if an electron is in any of these orbitals, like right there or right here, it has a certain ticket number. So for right now, I just want you to think about quantum numbers as like the ticket for the electron. So if an electron was sitting there, it would have a certain ticket. And that electron actually has that set of quantum numbers, which we'll show you how to determine that in a second. So the first quantum number in a set is the principal quantum number. So you saw in the previous slide that I had 3, 0, 0, plus 1/2 as an example. The principal quantum number is right there. It's that 3. So the principal quantum number is denoted by a lowercase n, and this tells me the shell. So this is what energy level the electron is. And I have an arrow pointing at that too, because if I'm using an orbital diagram, that's the principal quantum number. So if I'm trying to write a quantum number set for that electron, that arrow, its n would be 2. Now, if I had another orbital diagram I was looking at, every single one of these arrows has its own set of quantum numbers. So if I'm trying to write out quantum numbers for this arrow right there, it would have its own unique set. And this one would have its own unique set. They're different. So this electron's n value would be 2. Now this electron's on the same energy level, so its first number is also 2, etc. for all of those. So let's look at the second number. So the second number is called my angular momentum quantum number. It's represented by an L. I use a little cursive L. You can see it in italics as well. And this tells me the subshell. So this is telling me the shape of the orbital, and that is all dependent on what the letter is right here. Now I'll count on my hands for this, but 0 is S. So I start with a closed fist and I'd say S. And then 1 would correspond with P, 2 would correspond with D, 3 would correspond with F. And now that's where our universe kind of stops. So everything I showed you on the periodic table is going to fall in that beginning. Now you see in blue I have right here G, H, and I. These are theoretical states. If you end up in a college level class, they might ask you what the L value is, or the L value, what letter would it correspond if you were on like 6? And that would be an I. It literally goes alphabetical order after you get to F. So it goes S, P, D, F, G, H, I, J, K, L, M, N, O, P, etc. So how do I find my L? I look at the letter. It's a P, so it corresponds with a 1. The last thing to mention is this range right here. So L can only go as high as 1 less than N. So if my N was 3, then my L can go from 0 to 1 less than 3. So my L values could range from 0, 1, or 2. Which makes sense because I can have a 3S, I can have a 3P, and I can have a 3D, but there is no 3F. So I couldn't have quantum numbers that start as 3, 3. The third quantum number is called the magnetic quantum number, indicated by an m sub L, and that's all solely dependent on my L value. So in this example, I have a p. So that means my L is a 1. So since my L is a 1, my M sub L ranges from negative L to positive L. So I'm going to write those numbers underneath the orbitals. And that's telling me what orbital the electron is on, or what line it's on. So if I was writing out quantum numbers for that electron, its first one would be its n, would be the 2. Its second one would be a 1, since it's on the p sublevel. And it's on line positive 1. Now there's still one more that we'll talk about in a second. The last set, or the last quantum number, is called your spin quantum number, and it only has 2 possible values, plus 1/2 and minus 1/2. If it's spinning up, it's positive 1/2. If it's spinning down, it's minus 1/2. So back to that electron we were doing before. Its n was 2 because of the energy level. Its L was 1 since it was a p. It's sitting on line 1, and it's spinning up, so it would be a positive 1/2 for the spin quantum number. So that would be the set of quantum numbers for that particular electron. Now, if I was writing out quantum numbers for that electron, it would be similar, but it wouldn't be exactly the same. So the energy level's the same. The sublevel is the same since it's a p. It's on line negative 1, and it's spinning down, so that's a negative 1/2. Every single arrow would get its own set of quantum numbers. So here are some questions that you guys might see on a test or a quiz. So I wanted to give you some examples of what you'd be up against. So the first question asks us, write quantum numbers for lithium's outermost electron. So let me zoom that out. And let's do number 1. So I would draw the orbital diagram for it. So 1s, 2, and then 2s, 1. So I want to write quantum numbers for that electron, its outermost electron. So it's on the second energy level, so that's its n. Its L would be 0 since it's an s. And the M sub L would range from negative L to positive L. So since L's 0, it's negative 0 to 0, so it's on line 0. And it's spinning up, so that's positive 1/2. So let's try number 2. So would the following sets of quantum numbers agree with nitrogen's outermost p sublevel electrons? So it's giving me 3 sets of quantum numbers for nitrogen's outermost sublevel. So I'm on the 2p for all of these. So I would draw my 2p, draw those 3 lines, and let's fill in those electrons like this student did. So this first electron is on line negative 1, and it's spinning up. So that would be negative 1, 0, 1. So that would be right there. The second electron is on line 1, and it's spinning up. So that would be there. And the third electron is on line 1, and it's spinning down. So for nitrogen's outermost p sublevel, if I was doing this, I would have my 3 orbitals, 3 electrons, and I would have went up, up, up. So this is obeying Hund's rule. So whoever wrote these quantum numbers out did not obey Hund's rule, so those are not agreeing with nitrogen's outermost p sublevel. It should look like this. So this last set should read 2, 1, 0, plus 1/2. And then it would agree. Let's try number 3. So which of the following sets of quantum numbers are incorrect? So if I'm looking at that one, I'm on the 1s, line 0, And that's good. And it would be spinning up. So that is possible. So that's a good set. Now let's look at the second one. So I have 3, so I'm on the third energy level. My second number is a 3, so that would be S, P, D, F. And right from that information, on my periodic table, there is no 3F sublevel, so this is not a valid set of quantum numbers. L can only range from 0 to whatever n is minus 1. So since my n was a 3, my L can only go as high as 2. It could be 0, it could be 1, and it could be 2. It could be 1 less than whatever the n is. So I know that's not a valid set. Let's still check the last one to make sure that that's not incorrect as well. So I have a 2, S, line 0, negative 1/2. That one's good. That's a good set of quantum numbers as well. So the only one that was a problem was number 2. That one. Now for the last one, for number 4, it wants me to write out all the possible quantum numbers for n equals 2. So L, from this information right here, can range from anywhere from 0 to n minus 1. So since my n is 2, I could have 0, 1, and that's it. I can't go to 2 because my L always has to be 1 less than my n. Now my m sub L, the way I do that is I look at my highest L value, and then I do that negative L to L range. So negative 1, 0, and 1. And then my m sub s is always the same two quantities, so it's positive 1/2 or negative 1/2. If you have any other questions regarding quantum numbers, make sure to come and ask me in class tomorrow.